we're going to go ahead and talk about DMVPN Phase 3 in this section. That's our last discussion about DMVPN. We're going to take a look at DMVPN Phase 3. What are some of the design changes? And as we've talked about and seen, even going from DMVPN Phase 1 to Phase 2, what specifically is that impact on our routing protocols in this particular phase? What are the real advantages of Phase 3 over Phase 1 and Phase 2, and so on? We'll also take a look at this as we've done in the past with regard to Nhrp, EIGRP, Ospf, BGP, a little bit of on-demand routing. I may not get to that part here, but certainly something we talked about previously. We're also going to be using, in the case of Phase 3, much like Phase 2, multi-point GRE both on the hub routers and the spoke routers. So if we go into our command line here, this is the hub router. If I do a show run interface tunnel 0, just a recap since it's been a little bit since we've been doing this. In DMVPN Phase 1, very, very simple. On the spoke routers, we had a tunnel source and a tunnel destination statically defined. And that was, oops, sorry about that. And that's how we could tell whether or not we were running DMVPN Phase 1, because we had a static tunnel source and a static tunnel destination. In every case, whether it's Phase 1, Phase 2, or Phase 3, on the hub, we had this multi-point GRE tunnel interface on the hub, which allowed us to dynamically create those tunnels for each of the spokes that called home and registered. So we can see in this case that we are running DMVPN Phase 2 because we don't have static tunnel destinations identified on the peers. We have a multi-point GRE interface. That's going to give us the ability to run that spoke-to-spoke communication on demand as needed. Remember, the tunnels that go to the hub are permanent, they're static. The tunnels that go from spoke to spoke are dynamically created on demand, and they're only active during their use, if we say. So there are a couple of key distinctions between the differences of DMVPN Phase 2 and Phase 3 as opposed to doing manipulating the next hop attribute on the hub. What we do is we do resolution requests, and so in DMVPN Phase 2, if you recall, when I wanted to establish a spoke-to-spoke tunnel, one of the spokes had to send its traffic through the hub initially, and then the hub had to either maintain next hop information for the other spoke, or it had to redirect essentially traffic to the other spoke based on that. Okay, so based on the fact that we're talking to a different spoke. So we'll see how that changes a little bit in Phase 3. What are some of the implications with regard to the routing protocols? We talked about Ospf specifically and the DR-BDR election process. We had to have a multi-access network because the DR maintains the next hop reachability information versus point to multi-point. We rewrite that reachability information. Okay, so we're going to be using multi-point GRE on the hubs and the spokes, just like DMVPN Phase 2. We still need Nhrp. That's going to be required for spoke registrations to the hub. And then also Nhrp in this particular case is going to be required for spoke-to-spoke resolution. Unlike what we saw with DMVPN Phase 2, the key distinction in Phase 3 is what does the hub do when it receives some sort of resolution request for the spokes. So if a spoke wants to talk to another spoke, it needs to resolve or map the tunnel interface address to the underlay network, right? The physical address on the underlay network needs to be mapped to the virtual tunnel address on the overlay network. So the spoke is going to send an Nhrp query message to identify how to map those destination addresses, and then we're going to get a redirect message back to the packet source. This is Phase 2, right? So I send an Nhrp redirect message back to the packet source, and then I forward the original packet down based on my routing information base to the other spoke. So let me back up a little bit because I'm kind of mixing up some of the conversation here. If we were doing DMVPN Phase 2, that's where the redirect message comes into play, right? We send our initial resolution request over to the hub, and we looked at this in Wireshark as well. And then we get that Nhrp redirect message that goes back to the packet source. In Phase 2, we actually send our resolution request back down to the remote spoke. We saw that in our Wireshark capture as well, to define those mappings between the Nbma address and the overlay network address that we had configured as well. In Phase 3, there's a completely new type of route that gets installed in the routing table based on the spokes trying to reach each other. It's actually literally written to the routing table, and we'll take a look at that in our configuration here. Converting this operation over to Phase 3 is relatively simple. There's one command on the hub and one command on the spokes, but there is a completely different mindset in how we actually facilitate the routing in this case. It will depend on the iOS version that you're using. In older iOS versions, they used it as an entry in the Ceph table. So you would have to actually take a look at the Ceph, the Cisco Express Forwarding database, to be able to see those entries. But in newer versions, it's actually written as a route in the routing table, and it gets installed in the RIB, and you can actually see these routes based on the show IP route command. All right, so we're going to take a look at that. We'll take a look at how to inspect those routes, how to see if we're using optimal routing in this case, and if the resolution is working correctly. Just a couple of minor points to bring up. We did this in every one of our other DMVPN discussions. Summarization and default routing at the hub is supported because of, not because we're in this case, like DMVPN Phase 2, we're maintaining next hop reachability information, but in this case, we don't need to maintain next hop reachability information, which means that summarization and default routing at the hub is supported. And that's going to mean that for the Nhrp routes for spoke-to-spoke tunnels, we have more control and flexibility on how we can maintain that information as well. All right. The next hop is still modified from the hub to the spoke address. So we're still doing that modification. It's just that initial resolution is a little bit different. Okay. So if we looked at this behavior, say in Phase 2, where do we do summarization in Phase 2? And what the result of that is based on the next hop pointing to the hub means, all right, let me rephrase that. Okay, so let's say, for example, I am doing summarization in Phase 2. The next hop would point to the hub in that particular case because I can only do default routing and summarization at the hub. Now that might help in reducing the amount of routing information, network reachability information that's required for each of the spoke destinations, but it also would mean that I would not have the capability to do dynamic spoke-to-spoke tunneling between my spoke routers. Okay? If you look at the routing table from the spokes point of view, you need to verify the next hop. So let's take a look at what we have here. If I look at the routing table in R5, let me see what protocol we're running on here first. So it looks like we're running EIGRP. We've got BGP configured here as well. Oh, that's right. I was showing you guys the BGP option to do groups, right? Peer groups in BGP. I think we can kind of leave that in there anyway, because if you look at the administrative distance, well, these are, let's see how these guys are showing up here. Oh, I forgot one thing. Hold on one second. All right, sorry about that. I forgot when I reloaded this to update my interfaces. So I just went through, and what I did is I just cleared out BGP from each of my routers, and we're just running EIGRP now. We'll just start with a basic review of what we're doing here. So we are running Nhrp, of course. That's part of our DMVPN configuration, and we're running EIGRP process autonomous system number 1. Let's do that one more time. I forgot to put in the autonomous system number. Let's do no router BGP1 and send that over. There we go. All right. I just don't want to. I want to be confusing as we kind of go through the review. So if I look at the way that router 5 handles the traffic as the hub, if I do a show IP route, I should see each of the spoke subnets listed in the core router here. Now, if I do the same investigation, show IP route EIGRP on one of the spoke routers, I'm only seeing the traffic behind the hub. And that's because on my tunnel interface, I have to go into interface tunnel 0, and I have to do no IP split horizon EIGRP1. So I can get rid of the split horizon rule, and I should be able to see at least the remaining subnets for each of the other routers. Looks like we're missing router 1. Oh, no, I'm not missing router 1. I am router 1. There we go. So we are seeing all the spoke networks and so on. But notice the next top attribute for each of these, 10.10.10.5. Okay. Now we're running DMVPN Phase 2 in this particular case. So it's the next top attribute is being kind of, I wouldn't say necessarily maintained by router 5, but if I dig down a little bit further, show IP route 192.168.30.0, I can see that the routing descriptor block indicates that that router is the destination for that spoke. So if I do a trace route, for example, to 192.168.20.1, which is the subnet behind router 2, you can see that it goes through router 5 and goes to router 2. And we're not getting any kind of direct spoke-to-spoke communication. All right, we're just sending the traffic up to router 5 and over to router 2. So again, with DMVPN, there are some considerations. Obviously, the more complicated aspect of any kind of DMVPN implementation, this is what's going to trip you up on the exam if you're not really kind of familiar with it. I didn't even look at it for a week and a half, and I'm already struggling to remember the implications of running DMVPN Phase 2 with EIGRP. Of course, split horizon is pretty easy to remember, but in EIGRP, the next hop is not maintained as the traffic flows through the hub. So as part of the design and implementation, you have to go into the hub in a DMVPN Phase 2 configuration, and you have to say no IP next hop self. I did the split horizon, but I didn't do the no IP next hop self. So what I should see now, as I do this trace route, is those spoke-to-spoke communication is now allowed. And if I do a show IP route 192.168.20.1, I can see that I'm learning about the route from the hub, but the next hop attribute is being modified to the spoke IP address. That's standard behavior for DMVPN Phase 2 with EIGRP. All right. So when you look at the routing table from the spokes point of view, what we're really focused on is what is the interpretation of the next hop address from the spokes point of view. All right, that's the most important aspect. Is there a way to do summarization in Phase 2 where the end result is the next hop points to the hub? Of course, we can do summarization at the hub. But again, we're not going to be able to do any kind of dynamic spoke-to-spoke tunneling. All right, because if R1 wants to go to router 2, for example, R1 is going to go to router 5. Router 5 is then going to reflect that information back over to router 2. We're going to use EIGRP in this example. We'll take a look at some of the other protocols and their implication as well as when we move into Phase 3. But if you recall, BGP and EIGRP are great candidates for large DMVPN networks because their design is arbitrary. We can summarize at any point, and we can kind of manipulate how routing occurs at any point in the network. So that's what we're going to focus on, since EIGRP allows this arbitrary design. All right, so let's say on the tunnel interface on the hub, we summarize to a default address. Obviously, in this particular case, it's not really going to save us much because we only have 3 spoke subnets that we're concerned about. But let's say there were 10,000 different spokes, and now we're trying to summarize these 10,000 routes, right, between the different spokes. The way that that's going to look is that we are going to basically just create a summary address in EIGRP1 on the tunnel interface of router 5. So let's do IP summary address EIGRP1 quad 0 with a quad 0. Oops, did I get that right? Yeah, quad 0. Now if I go back to router 1, show IP route EIGRP, we can see that we're just getting a default route. Now if I do a show IPsef 192.168.20.1, we can see that we're using that default route to route to the destination. There's a reason why I'm kind of pointing this out, because in DMVPN Phase 2, it essentially breaks spoke-to-spoke communication capabilities. But in DMVPN Phase 3, this is actually allowed because of the Nhrp redirect option. We don't really care whether or not we have specifically defined destination addresses for the destination prefixes. So if we look at the routes on the spokes, doesn't matter which spoke we look at, and every one of these spoke routers, all we're going to have is a default route to the hub. We still have reachability to the destination, but because the next hop points to the hub, and the next hop is the hub itself has reachability to each of the spoke destinations, we're basically forcing the hub to be part of the data plane path in this particular case. So if I come in here and I do a trace route, where's my mouse? Right here. There we go. Trace route to 192.168.20.1. Again, we're going through the hub. So we still have reachability. And in small designs, this is maybe not as much of a concern, especially if you want to route all the traffic through the hub for other security reasons. This would not be a huge concern. But obviously, this is the by definition where summarization is not allowed. Default routing is not allowed in DMVPN Phase 2. In DMVPN Phase 1, it is allowed. Because guess what? In DMVPN Phase 1, all the traffic has to go through the hub anyway. So we basically made our DMVPN Phase 2 configuration look like DMVPN Phase 1. All right? In DMVPN Phase 3, we have 2 specific configuration changes that have to take place. One of those changes is going to be on the spokes, and one of those changes is going to be on the hubs. On the hub, we have to indicate that we want Nhrp redirect. So when someone sends me, say for example, an Nhrp resolution request, I'm going to send it back to the destination spoke and show them or tell them how to do a direct resolution. On the spokes, we need to allow those spoke routers to install those updates that are pushed from the Nhrp process, and we use the IP Nhrp shortcut command. We only need that on the spokes where the Nhrp routes are going to be installed. So if I go into router 2, let's take a look at something here before the configuration, and then we'll take a look at something after the configuration. If I go into router 2 and I do a show IP route 192.168.10.1 as an example, 10.0, sorry, we can see that there's no reachability to that particular prefix. If I do a show IPsef 192.168.10.0, I can see that that's going to match the default route for path resolution. Now, because we have, or we will have, excuse me, the shortcut command, basically what's going to happen is this is going to instruct the spoke router to generate an NHRP request to figure out what the actual destination is and what the underlying Nbma address is as well. So let's go ahead and implement our configuration changes. Like I said, on the hub, we need to do, under the tunnel interface, let's do a show run interface TU0. So you can see it's not here, right? IP redirects, that's a different concept than NHRP redirects. But notice here we don't see the IP NHRP redirect command. So let's go ahead and add that. All right, and then on each of the spoke routers, we're going to want to add the NHRP shortcut command. All right, so config T, interface tunnel 0, IP NHRP shortcut. And right. All right, so that's the configuration that needs to be applied to each of your spoke routers. So if you're doing a, if you're taking a look at your tunnel configuration for the spokes and you see this NHRP shortcut command, you know for a fact you're running DMVPN Phase 3. If you see the IP NHRP redirect command on the hub, you're running DMVPN Phase 2. Phase 3, sorry. If you see multi-point GRE on all of the interfaces and you see the appropriate configurations necessary to do the next hop manipulation, you're running DMVPN Phase 2. If you see statically defined source and destination tunnel configurations on the spokes, you're running DMVPN Phase 1. All right. And there's kind of, like I said, again, there's kind of ways to trick the router into behaving like a specific phase, even though your intent was maybe to configure it as Phase 2. I think really the only one that would apply to is DMVPN Phase 2 acting like Phase 1 with the default routing and all that. Okay. So let's go ahead and run a debug, and let's take a look at the process of resolution that's going to take effect. Let's actually run the debug on router 2. Router 1. Let's just run it on all three routers because we're going to create a communication channel between router 1 and router 2. Router 5 is the hub. Router 1 and router 2 are the spokes. We're just going to do a basic debug NHRP. All right. Let's see here. So let's go into those three routers. Router 5, router 1, and router 2. And we're just going to do an end, a write, and debug IP NHRP. Let's just do debug NHRP. I think that's the right command. All right. All right. So let's go ahead and do a ping from router 2. Remember, when you're doing a ping on the exam too, especially if you're testing NHRP, put in your destination address that you're going to ping, but make sure you source it from the LAN side. Otherwise, it's going to attempt to use because we have that default routing in place. It's going to attempt to use the Nbma interface to route the traffic. All right. So let's go ahead and do that ping, and let's see what we see. All right. So we see obviously a lot of NHRP traffic happening here. Let's go ahead and do our undebug all. Get rid of all that. All right. And let's just kind of take a look at what's happening here. So the NHRP process was triggered as soon as I did the ping. To get to router 1, we need to use the Nbma address. And we can see that with the PA key SRC address here. Let me find it here. PA key SRC. So here we're receiving information that says we found the node for routing. We're looking for routing to this specific destination. And what I'm looking for specifically is the route lookup process using this tunnel source address. So we're on router 2, that's our tunnel source address. And we're doing a NHRP, there it is. We're sending an NHRP resolution request for 192.168.10.1 using our tunnel source of 10.10.10.2. All right. So we've encapsulated the data. Our Nbma address is 209.165.200.245. And what I should see is, as I progress down the list here, is I should see a response indicating what the destination Nbma address is for that particular, there it is right there. That's the Nbma address for that particular destination. All right. Now, there is a kind of a difference in this case about the reply as opposed to what we would normally see with like DMVPN Phase 2. The reply in this case is for the actual destination. It's not for the next hop value, right? So in DMVPN Phase 3, we're actually trying to resolve the actual destination. Think of it as kind of like, well, yeah, I guess you could say it's kind of like a proxy ARP in Ethernet, for example, where you're trying to resolve a destination, but you don't have the next hop MAC address, if you will. So we need to essentially create one or identify one. All right. When you look at the destination, or if you point, for example, the default gateway in a proxy ARP scenario, you point your destination traffic to the default gateway, you're essentially going to generate a proxy ARP for every single destination that you go to. Now, from a topologies perspective in this particular case, router 2 doesn't know where router 1 is. And whenever I try to reach that particular destination or any other destination that I don't have any information for, that's going to trigger an NHRP lookup. All right. Now, if I do a show IP route, previously I did a show IP route to 10.1. Let's go back up and take a look if I have it here. I did a show IP route to that destination right here. So show IP route 192.168.10.1, the network was not in the RIB. We were matching the default route for Ceph, but the network was not in the RIB. Now if I do a show IP route 192.168.10.1, I can actually see that I have a destination identified, and it is the overlay address for the tunnel interface on router number 1. So NHRP actually installed this special type of route called an Nhrp route. And we can actually investigate this even further. We've got a route installed that was installed through the Nhrp process. So basically we're asking the hub that's running Nhrp, and we're sending an Nhrp resolution request, if there's a shorter path for the particular destination in the data plane. We're still going to use the hub in every case as our control plane function. But at the data plane, we're going to try to route to the specific destination. Now, if I wanted to see what the underlay address is for the matching route, show IP route doesn't show me the underlay address. In fact, if I do a show IP route just in general, you can now see that we have some H routes in place. These H routes indicate NHRP routes that are installed. HSRP. Yeah, these are representing NHRP routes that are installed. All right, we can see they're mapped directly to the tunnel interface. Now this one here is the mapping for the overlay tunnel interface, and this is the mapping for the destination prefix. Also notice here that we have some different values here for administrative distance and the metric. Okay, so that's slightly different as well. We'll get into maybe a little bit more about that in a different lesson. We're going to talk more about NHRP with specifically not focusing on NHRP, but its relation to routing protocols. All right. So rather than showing this as an EIGRP route, because we're running EIGRP in our network, we're not resolving this route through EIGRP. We're resolving the default route through EIGRP, but we're resolving the specific prefix destination through NHRP. So it gives us the ability to do summarization. And these temporary NHRP routes, they're not permanent, right? So if I come in here and I do a show IP route, we can see we learned about this route 6 minutes, 31 seconds ago. Now there's no indication here as to the age of this particular route. Remember, these are on-demand circuits from spoke to spoke. So this is not a permanent route. Now the question is, what happens? How long is that going to stay in place? And the other question that I have is, how can I determine the Nbma address, because I'm not seeing the Nbma address that was installed during the NHRP process. So if I do a show IP NHRP 192.168.10.0, I can see now the underlying Nbma address that is utilized to encapsulate the GRE traffic and further encrypt it and so on. So the tunnel was created 7 minutes ago. It's going to expire in 1 hour and 52 minutes, right? Those are countdown timers. You can see it's going down 27, 26. So that's 1 hour. I think it's 2 hours by default. It's actually probably, yeah, it should be 2 hours, yeah. Because the tunnel was created 7 minutes and 35 seconds ago. Yep. So the default age is about 2 hours. After 2 hours, if traffic hasn't been sent back and forth using these destinations, that tunnel information and that route will be removed. So basically all we're doing in this case is we're asking the hub with NHRP if there's a shorter path for the data plane. In phase 2, we're trying to resolve a next hop address. And specifically, we're trying to resolve a next hop address on the tunnel interface. But in phase 3, we're trying to resolve our final destination. The end result is that we have a default route at the hub, but spoke-to-spoke traffic is going to trigger an NHRP resolution request to find the best data plane path, to find the best direct path to the destination. I mean, how does this affect us from a design perspective, right? From a network design perspective, it's really simple because we just have to default to the hub and then we resolve to find the actual destination of our remote spokes. We don't have to have massive routing tables, and we don't even have to really, frankly, do any kind of dynamic exchange over the DMVPN network. All right. We find the match with the NHO. That's NHO is our next hop override, which allows us to identify what the actual next hop is in the destination. So it's really, really simple to convert from DMVPN Phase 2 to Phase 3. Now you also see from a real design perspective here, and from a scalability point of view, obviously it's going to be better to advertise a default route down to the spokes, and then we'll just do whatever spoke-to-spoke resolution we have to do on demand, rather than having massive routing tables that statically define all of these spoke-to-spoke destinations. You actually may have a case also where not all the spokes have to talk to each other, right? So there might be a limited case where you may have spoke 1 and spoke 2 that have to talk to each other constantly, but nobody ever has to talk to the other 1,000 spokes that exist. So this allows us to incorporate that efficiency of not advertising routes for every destination and only doing the resolution on demand. Okay? Like I said, only 2 changes from a configuration point of view. How does this affect us in Ospf? It's wonderful in Ospf because in Ospf we had to design our DR-BDR election process, or define the DR-BDR election process based on next hop resolution and overriding or maintaining next hop information. So in the case of EIGRP here, I had a configuration in place on R5. If I do a show run interface tunnel 0, interface tunnel 0, and if I take out split horizon or add split horizon, and basically just kind of recreate the default behavior. So I'm not I'm allowing next hop override, and I'm also disabling split horizon on the interface. Do I still have resolution? So if I ping 192.168.20.1, I can reach it. And if I do a show IP route 192.168.20.1, I can see that I'm not using the default route, but I'm actually using the destination. Show IP Nhrp 192.168.20.0. So running DMVPN Phase 3 eliminates a lot of the design considerations that have to be taken into account when you're running Phase 2. If you want spoke-to-spoke communication, there's really no reason to ever run Phase 2. You should always run Phase 3. If you want just a standard multi-point to multi-point hub and spoke design, then you should just run DMVPN Phase 1, right? Because there's no reason to do any kind of spoke-to-spoke resolution. I guess the bottom line is don't ever run DMVPN Phase 2. Okay? So point to multipoint previously only supported in DMVPN Phase 1. We could do point to multipoint in Phase 2, but the spokes would not be able to dynamically resolve each other. And we had limitations in implementing OSPF or EIGRP or other protocols, even BGP. We had to use a route reflector and so on. But now that we have override, and Nhrp is going to basically point me to the right destination, I don't have to worry about any of that stuff anymore. It's all just going to work. All right? So even though the next hop might point to the hub, in either a case where you haven't implemented the right topology, or you're not using the right endpoint types, or you haven't implemented the split horizon rules and the next hop self rules, the hub is eventually just going to override wherever you're supposed to go to, and it's going to point to the route to the spoke. All right. So we might see initially that packets will go up to the hub, but then packets will eventually go directly from spoke to spoke. All right. We actually saw this behavior before in DMVPN Phase 2, but it wasn't with next hop override. It was essentially directly related to resolving the next hop, but in DMVPN Phase 2, the next hop value gets set by the original spoke, and it gets preserved by the hub. All right. So, the options I had in that case were, do I want to drop the traffic, or do I want to route it with a suboptimal data plane for those initial packets? Now, you can do that. You can actually set that up to say, okay, almost like doing an ARP request, where kind of the initial ARP request or the initial packet is going to get delayed or dropped as we go through the ARP process. Do we want to route that initial packet through the hub, even though it's a suboptimal data plane, or do we want to drop that initial packet, in lieu of, during the process of doing the resolution? Most people will simply allow it to route through, because the packet's already made its way up to the hub anyway. All right. So if I was running, trying to think if I can recreate this. Let's try to recreate this. So let me go into all of my routers here, and let's do a NOAA router EIGRP1. And let's do router OSPF 1. And let's just make it a flat network. No, we don't want to do that. Let's do network 10.10.0.0. Area 0, and we'll do our LAN side. All right, so basically we're going to get rid of EIGRP. We're going to go ahead and implement OSPF. Now, if this was DMVPN Phase 2, I would have a concern. I would want to make sure that my OSPF network type is multi, some sort of multi-access network, like a broadcast network or Nbma. But I would definitely want it to be a multi-access network, and I would want a DR/BDR election. And on top of that, I would also want to ensure that the hub is going to be elected as the DR so that we can maintain next hop or preserve next hop information. So let's wait for our relationships to load here. So it says here that router 5 is the DR. I'm actually going to clear the process on router 5. Actually, before I do that, let me make sure I didn't have any residual configurations on the tunnel interface with regard to OSPF. I do, all right? So these were the commands that I had to apply in DMVPN Phase 2 in order to apply a OSPF network in this point-to-multipoint environment. Because we want to make sure it's a broadcast network, it's not point-to-point or point-to-multipoint, and we wanted to make sure that the spokes never became the DR. So let's go ahead and take that out. All right. Config T interface tunnel 0, no IP OSPF network. Actually, let's do this. Let's just make it, yeah, that's fine. Let's do this. IP OSPF network point to multipoint. Oops. Tab completion does not work in this, by the way. Point to multipoint. And let's do no IP OSPF priority. I want to make sure they're all at least point to multipoint because the timers won't match up otherwise. So we'll do that. All right. All right. Show IP OSPF neighbor. So now we're not doing a DR/BDR election, right? And that would normally, let me go to router 5 and do this. That would normally mess up this next hop attribute. Show IP OSPF neighbor, all right. Show IP route 192.168.10.0. Okay, yep. Next hop is 10.10.10.1. Now let's take a look at one of the spoke routers. Show IP route 192.168.20.0. All right, so next hop is router 5, which is what we would expect because we're not preserving next hop information from the hub. The hub is rewriting that next hop information. So if I do a trace route to 192.168.20.1, we see the traffic goes through the hub. Now what we should see in this case, which I'm not, why is it not doing? So this is strange. I am getting a next hop override. That's what the percent sign indicates here. But the next hop override should point to router 1 in this case, not router 5. That's what I'm trying to figure out here. Why is it pointing to router 5 and not router 1?
You still have a default route on router 5?
That was in EIGRP. That was a summary that we were creating in EIGRP.
Got it.
We got a redirect. We got our NHRP shortcut. Let me just try one thing. I'm probably running into a... Let's clear... let's not do that. Let's do this one. Clear IP route. Show IP route. Next hop 10.10.10.2, 10.10.10.3, 10.10.10.1. I would expect, in this case, to see these routes all pointing to 10.10.10.5. That's not a problem. But what I should see for these destinations is my next hop override. So if I do a trace route to 192.168.10.20.1, show IP route, I'm getting my override, but for some reason the override is pointing to 10.10.10.5. And I'm not sure why it's doing that. I'm going to try one other thing here. Config T, interface tunnel 0 IP Ospf network broadcast. See if that helps. Wait for that to come up. Normally, there is the routing table feeds into the forwarding table, which is how you would route. Basically, in the case, what I'm trying to demonstrate here, if I did a show IP route, it's going to look like, to the destination, 10.1, it should look like the route is known through OSPF. But if I do a show IP Ceph, it's different, right? So let's see if it's, let's do a ping 192.168.20.1. If I do a show IP route, 192.168.20.1, so we are seeing in this case, it's showing that it should, the next hop is 10.10.10.2. Okay, there we go. So it's working now. For some reason in point to multipoint, it wasn't doing the next hop override appropriately. I'm not sure why that was the case. Let me see who the DR is. Router 5 is the DR. Let's kill that. Oops. And do a show IP OSPF neighbor, show IP OSPF interface tunnel 0. So in this case, the DR is now router 3, and the BDR is router 5. So let's kill it one more time. Clear IP. Trying to get it so that it's neither the DR or the BDR. Show IP OSPF interface tunnel 0. Yeah, it's okay. Still the BDR. I'd have to kind of, let's do this. Shut that down. There's a wait period that you have to go through in order for me to lose my role as the BDR. It's about 40 seconds. Normally, like I said, the routing table feeds into the forwarding table, but we're using an override in this particular case. Remember, the RIB and the FIB don't agree, basically. And in this case, this is actually just a hack that Cisco created to support DMVPN Phase 3, is to have this disconnect between the RIB and the FIB. I'm not sure why it didn't work in point-to-multipoint mode. but it seems to be working in broadcast mode. So let me do a show IP Ospf interface. Tunnel 0. And looks like we don't have an adjacency just yet. We're still in the waiting state. You can see that right here. That'll take a few seconds. So we're kind of trying to figure out whether or not we should be reclaiming a particular role. Most people say that OSPF DR and BDRs are non-preemptive. They do actually have a preemptive status. And you can see that Router 5 actually did preempt OSPF and became the DR in this particular case. And then it's still trying to figure out who the BDR is going to be. My point in doing this, I'll just make it the BDR, that's fine. My point in doing this, though, is to indicate or to show you guys that maintaining the spoke or the hub as the DR is not necessary with this next hop override option that we have with DMVPN Phase 3. All right, so I'll let that kind of converge, and then we're going to take a look at the disconnect between the rib and the fib. If you don't actually understand what that disconnect is between the rib and the fib, you need to understand it, because when you're doing your troubleshooting, you might think that the router's doing one thing when in reality it's doing a completely different thing. And always investigate the rib and the fib together, right? Do a trace to the destination, it doesn't make sense because the routing table says one thing, but then Ceph says something else. All right, let me show you. All right, well, I'm the DR. Okay, that's fine. Whatever, we'll leave it that way. Show IP, OSPF neighbor. Why are my adjacencies not forming now? IP OSPF network broadcast. I think I broke my tunnel information. Show IP. I think I'm going to have to shut down all my tunnel interfaces and bring them back up. Kind of broke. I was messing around. Let's do interface tunnel 0. Shut. No shut. And right. We'll just bring them all down and bring them back up. All right. Had to restart all my tunnel interfaces. So what I wanted to show you here is that disconnect between the rib and the fib. If I do a show IP route 192.168.20.1, 20.0, excuse me, I've got this OSPF route that indicates that I'm going to go to 10.10.10.2. If I do a show IP Ceph 192.168.20.1, it indicates essentially the same value. It wouldn't do that initially. I already did my ping, so it already did the resolution. Wouldn't do that initially, but the routing table would normally say one thing, and then the Ceph table would say something else. Like I said, if I do a show IP Nhrp, that's going to show me the Nbma destination as the RIB next hop override value. This actually turns out to be one of the scaling limits of Phase 3, because it's going to depend on how many prefixes you actually have, or you're actually routing packets to. If all of the traffic is spoke to spoke, then you're going to have a whole bunch of different next hop override entries. It's kind of a little bit out of the scope of what we're doing in this lesson. We're about to wrap up tonight's lesson, but there are some scalability numbers to keep in mind if you're going from Phase 2 versus, or looking at Phase 2 versus Phase 3. And any spoke that doesn't have that IP Nhrp shortcut command means that the spoke is going to be running through the hub on the outbound path, but the return would be direct. So there's an asymmetric aspect to the routing as well. All right, if I did a trace route, for example, in both directions, I would see that the trace route went through the hub initially, But then when I did a trace route in the opposite direction, I would see a direct spoke-to-spoke communication. There is a document on Cisco's website. It's called Migrating from DMVPN Phase 2 to Phase 3. And it talks about real design point capabilities and what are some of the limitations and so on. It really is going to depend, though, on the physical boxes, whatever code you're running on the platform, and so on, based on how the routing design is going to look. All right. In any event, if we're running DMVPN Phase 3, if I do a show IP route, I should see, let me do a trace route, 192.168.20.1. I should see in this case, now why am I not seeing my override? We saw it before, and I think in this case, because we didn't have to do the override, we should be seeing a % for if the route was overridden. Older versions may not show this. I know that this particular version of software does show it because we saw it in one of our previous examples. But this is only going to be done for routes that we're actually trying to forward to. In our particular case, though, and I have a feeling it's because of the configuration of router 5. Let me try one more thing. I don't know if this is going to work or not, but let me try it. What the heck? IP, Ospf. Yeah, that's not going to work. If router 5 is not the DR in this particular case, we're not going to be able to form any adjacencies because even with DMVPN Phase 3, multicast, spoke-to-spoke multicast traffic is not allowed. So I can't really trick it that way. I suppose I could go back to point-to-multipoint. We saw this previously. Let me try it one more time. Let me go back to point-to-multipoint. Interface tunnel 0. Shoot. Multi, I'll get there eventually. All right, let's go back to router 3, show IP route 192.168.10.1. Okay, so learning about it from router 5. Actually from router 1, but the next hop is router 5. If I do a show IP route, there we go. The reason why we were not getting it in the broadcast mode is because we weren't overriding the next hop. Because the DR in the case of OSPF broadcast mode preserves the next hop information. I had to create this override, if you will. So this is where the difference was to show you is that the routing table indicates that we're supposed to go to router 5. So if I do show IP Ceph for 192.168.20.1, we can see that the next hop is listed as 10.10.10.5, 192.168.20.1, and let's do show IP route. We got an override for that particular destination, right? So we're saying, okay, if you want to get to 10.10.10.2, send the traffic to 10.10.10.5. Trace route 20.2, 20.1. Yeah, something's not. Yeah, I'm not sure what's going on here because I did a debug and we are seeing the resolution here for the destination, 243, 242. For the tunnel endpoint, we are getting the override for 10.10.10.2, but it's still pointing to 10.10.10.5. Not sure why it's doing that. Because all the traffic is still traversing at the data plane, all the traffic is still traversing the hub. I'll take a look at this and play around with it a little bit later on, and see if we can't figure out what's going on here. But let's go ahead and wrap up. I just want to talk about a couple of other things here before we kind of wrap up this lesson. The analysis on the data plane should indicate that we're overriding the route and going directly to the other spoke for that data plane traffic, but not sure why that's not happening. Anyway, that's something that obviously I'll have to fix, and I'll probably bring it up in my next lesson, before we start our next lesson anyway. Depending on how many spokes you have, if we add IPsec on top of this as well, there's going to be a huge scaling limitation with crypto, because if I have a bunch of different spokes, I may not, at the hub at least, I may not be able to rekey all of my spokes appropriately in order for them to communicate, because that's going to require a lot of CPU cycles, a lot of CPU. We're doing that prime number generation or generating of those large prime numbers for the key rekeying. So in the case of very large IPsec VPN scenarios, we probably want to look at something like get VPN, because you're going to create a group tunnel and share the group encryption key, and they're going to all use that same encryption and decryption key. The hub is going to be always present in the control plane, and which is the case for pretty much any VPN that we've talked about, all the DMVPNs, and so on. So default configuration from a scalability standpoint, in our configuration, obviously we're not going to have any scaling issues, but as you grow, you may have to consider looking at a different VPN technology. All right, like I said, the default expiration timer for the spoke-to-spoke tunnels, those on-demand spoke-to-spoke tunnels, it's about 2 hours. You can tune that value. And also remember, as we're going through these debugs and kind of looking at everything, NHRP is not a function of DMVPN. DMVPN is actually a function of NHRP. I know that's kind of a philosophical way of looking at it, but actually in reality that's the way it is. Huh?
That was really deep.
I know, man. It's just amazing, isn't it? A lot of times what people will do in order to maintain spoke-to-spoke communication beyond the 2 hours, if they don't want to have to keep doing the resolutions, is they'll just generate some interesting traffic using IPSLA or something like that between the endpoints, between the spokes, so that we never hit that keep alive timer of 2 hours. All right. It's going to bug me. I'm going to play around with this a little bit, try and figure out why it's not doing the override correctly. I probably misconfigured something, but or Ospf is doing another reason not to run Ospf over a DMVPN. It's doing something obscure that I'm not aware of. So I'll take a look at that, investigate that. But NHRP shortcut on the spokes, IP NHRP redirect on the hub, and you get yourself DMVPN Phase 3. All right. So we'll see you guys on Wednesday, where we're going to start doing our route manipulation.